All right, today is the last lecture before we start presentations, and hopefully I'm going to have 15 minutes for our first presentation. The presentations next week, you're going to get an email from Subic the night before who's going to speak next day. So we're not going to send you today so you can relax for a month and say, I'm the last, or can you put me the last, okay? There is no such a thing. We are going to do it randomly, and you will be notified on Monday, okay? Now, you can maybe buy Subic dinner or something like that, and that's his own business. Okay. So the first actually presentation we're going to have later on today is on Gaussian processes. So in the context of, you're going to be doing some variational things as well?
One slide.
One slide, okay. So originally, so basically to be able to do sparse Gaussian processes, you have to go through variational approximations, which we didn't have time to cover in this course. So I'm going to give you an extremely rapid pace with one or two examples of variational inference. The slides are actually of the order of like 150 to 200 with lots of examples, so you need to read them. There are only some minor symbols in the equations in maybe 4 or 5 slides that I'm going to try to correct them by tomorrow, right? But you can consult them for further details. Okay. All right, so if you remember, so we're looking for problems basically where we have some observations x, okay? And there are some latent variables z. We discuss the context of latent variables both for supervised learning and unsupervised learning and doing mixture of models. You know, so we have seen different scenarios on this, and basically the EM algorithm was built around approximations to allow us to compute this posterior distribution. So today we will discuss some other methods, okay? A whole new class of methods. And we're mainly interested in problems where this distribution is computationally expensive to compute. It's maybe there is no analytical approximation, and the problem is high dimensional. You have lots of data. So things where maybe the EM algorithm, it will not be of practical use. Okay, so there are two methods there are multiple methods already. We have seen some of them, right? One of them is if you don't really have any way to analytically approximate the posterior, would be to use samples from the posterior, all right? So you can think with samples, you build some empirical measure of the posterior distribution. We didn't really cover sampling methods in this course. We discussed this in earlier course, but you can imagine that maybe taking samples from the posterior is easier than actually having an analytical approximation to the posterior. So we're not going to do this today. What we're going to do is a deterministic approach, going with the name Variational Bayes or Variational Inference, where with some assumptions, we're going to try to analytically approximate the posterior distribution. In particular, we will be interested in problems where the approximation of this posterior assumes a certain factorization that, as we will see, it very much relates with ideas from statistical mechanics, okay? So we will try to discuss some of those things. You may say, well, where is the Laplace approximation belonging? Because, you know, in some of the problems, we actually use the Laplace approximation for this. Well, so the Laplace approximation is a local approximation, right? You go and fit a Gaussian on the top of the mode of the posterior. So you have to calculate the mode and the curvature, and you fit a Gaussian. So what we will do is we will discuss global approximations that hopefully will be way better than the Laplace approximation. All right. So the algebra that we will actually use, we already have seen it, and so we need to only revisit it to see exactly what the setting is. So if you remember this wonderful identity, the log likelihood, log of p of x, it was this lower bound, okay? And we give reasoning why this is, we call it a lower bound, plus the KL distance between Q and P, where Q in principle is an arbitrary distribution, okay? And we call this a lower bound because you can see from here, since this KL thing is greater or equal to 0, so the log likelihood is greater or equal to this L of Q. So maximizing L of Q will actually solve our problem, because maximizing L of Q will be the same as minimizing this distance of Q and P, which in principle means that this arbitrary distribution Q is going to be used as an approximation to the exact posterior P of Z given X. Okay? But this is the identity that is valid for any arbitrary Q. Okay? So pay attention to the notations here. So this is the KL distance of Q from P. This is a non-symmetric distance. Easy way to remember, minus sign Q and Q. Okay? And here is log of P of Z given X. And this lower bound is the expectation, basically with respect to Q of Z, of the log of the joint distribution of X of Z divided by Q of Z. Actually, if you know, this Q log of Q gives you minus the entropy, so really the term we're interested in is Q log of P of X and Z. This is what we will use. All right, so this slide has the proof, and I am not going to repeat the proof. We did this in an earlier lecture. Okay. Okay, so there is actually, let me just put the whole of the slide up, because since we talk about variational methods and we want to see similarities of these variational methods with other fields in mathematics and physics, you can pose different sort of equivalent formulations of the lower bound. And so we want basically to maximize the lower bound or minimizing minus the lower bound. So if you use the definition of the lower bound, minus L of Q, all right, this is the definition. Q log of Q with a minus will give you the entropy of Q. And then from the numerator, you get minus Q log of P of X and Z. So this is the expectation of the log of the joint likelihood of X and Z, all right? I'm writing it here like that. So if you actually do the following definition, if you take the log of P and you define it as minus some energy functional, right? Just a definition, I should put 3 lines there. If I define this as minus this energy functional, so really what you have here is you have the expected value of this energy with respect to the distribution Q minus the entropy, which is from thermodynamics and statistical mechanics, is nothing else but the Helmholtz free energy. Okay? So effectively, minimizing the Helmholtz free energy is the same thing as maximizing this lower bound. So effectively, people in machine learning discovered what people in physics knew for more than 100 years now. Okay? And for various other applications, you can actually come up with alternative formulations. So if you use these things in the context of different variational methods like variational autoencoders, you may put this in a different setting, but bottom line is whatever you do, this is what, come on. That's the bad thing on having this thing clicking like that. So whatever you do, it's really this equality that you're using, and effectively we're going to be maximizing to find an approximation to the posterior distribution of Z given X. We're going to have to maximize L of Q for arbitrary distributions Q. All right, nothing new yet, okay? All right. So let me, I think this we may have seen this example before, but let me introduce it, even though we haven't said anything about variational approximations yet. But let me introduce you to an approximation of a distribution that will give us a result that is different from the Laplace approximation. So imagine that you have this weird-looking distribution with some exponential, some sigmoid here. The variable is z. And we want to approximate this with the Gaussian distribution. So our Q of z is this Gaussian distribution, and we really want to follow this maximization of the lower bound to actually, with an approximation that looks like this, to go and compute the mean and the variance. Okay? So this is not a Laplace approximation, right? With the Laplace approximation, you will go and find the mode of this distribution, find the curvature, then fit the Gaussian, and if I suppose this must be the real distribution here, all right? So this, what is this, a red color? It's red, all right? So that red curve is the Laplace approximation, but if you do this variational approximation, if you assume Q of z to be like that, you're actually getting a distribution that's way different, okay? In this particular context, of course, you may say, wait a second, I'm much happier than the Laplace approximation. You notice the Laplace approximation nicely captures the support, captures actually the situation around the mode of the distribution, but this variational approximation is more global, right? You can see actually the support of the variational approximation is much bigger than the support of the, especially over here, the support of the Laplace approximation. Okay. All right. Here is our first approximation to get this new concept of variational Bayes methods. We're going to approximate, so the posterior, with a distribution Q of z, and we're going to assume that the distribution Q of z factorizes over the latent variables. So you remember, for example, lots of problems, we discussed, there was one latent variable for each data point. So you can have m equal to 1,000 or 10,000 or 1,000,000. So you're gonna, even though this is a joint distribution over many variables, you're gonna factorize it like that. Okay? And you can start questioning, yeah, but this is not good, Well, it is good enough. Okay? If you know something better, tell me. Okay? So that's an approximation. And obviously it's an approximation that may give interesting results that may allow us to rediscover things already known for 100 years. So this is the factorization we're going to assume for the approximate distribution. And actually I can tell you that the framework will lead to what is called the mean field approximation in statistical mechanics. So let's see, why is that? Okay? So what I am going to do is I'm going to plug in this factorization in the lower bound. Remember, the lower bound was the expectation of the log of p of x and z divided by the log of z. So I approximate log of z, and here is my, log of q of z, which is the summation that you see there. This is q of z, so there's nothing new there. All right? So I'm going to try to come up with a computational scheme that updates one factor at a time. Okay? So we're going to try to isolate one factor and see if we can write equations that allow us to update one factor at a time. So what I'm going to do is, in this product here, I'm going to isolate only the term qj. So the rest of the terms, I'm going to put them inside here for I equal different from j. Okay, and then I can do this times that. I can do the same thing. I can isolate all the terms that don't depend on j, and then there's only a singular term that has q of j times log of q of j. So this will be the entropy, basically, of zj. All right. So nothing yet. Okay. So this big parenthesis that you see here, I am going to call it log of p curly of x and zj. And remember, there is no Zj coming on these terms here, but there is a Zj coming inside there. And also don't forget that this term here integrates all the z's, but what z we leave out? We leave out Zj. Okay? So this is a function of Zj, so we call this whole integral log of p curl x and Zj. Okay? You will see in a second why we call this a log and not a probability, right? I mean, this, you can appreciate this looks like a free energy term. It's an integral there, right? So we will call this log of p curly. And minus qj, log of qj, these terms don't depend on qj, so we don't need them, okay? Now I am going to rewrite these two terms together. Will you agree with me that this is the k minus the KL distance between qj and this p curly of x and zj? Can you see that? What's the KL distance, right? I put a minus because it's supposed to be minus of qj of log of this divided by log of that. All right, so it will be minus the KL distance of qj from this p curly that I define, remember it through this whole bracket there. So what do we want to do to the lower bound? We want to maximize it, right? So we want to maximize it here means we need to minimize this distance between qj and this p curly, and we know what the exact answer is. The exact answer is when qj is equal to p curly. All right. Okay. So again, what is this quantity we define here? We said log of p curly is this integral where all the other factors have been integrated out. So effectively, what this integral is the log of the joint likelihood of x and z, but with all the variables except variable j integrated out. So effectively, what we are going to do by setting qj equal to this p curly, we're going to compute qj in the average field of all the other variables. Right, that's mean field approximation. You know, you look what one electron does in the average field of all the other electrons. So effectively, this is what we have here. We have the expectation of the joint log likelihood with respect to all the other variables. All right, that defines this p curly of x and zj, and that will be used to update qj. So the log of qj, basically what we get, log of qj is, remember, you know, we said qj would be equal to that, right? So if, this is e to this thing, okay? So I can write this in two different forms. Log of qj equal to this expectation, or if you like it, if you normalize it, this is the final answer, okay? So what we have is, we have an algorithm that says, look, approximate q of z with some factorization, one term for each latent variable, and then update each of the approximate distributions for each of these latent variables one at a time in the average field of all the other variables. Which means to compute qj, you need to know what the other variables are doing. So what's the algorithm going to be? How do we compute in all these factors? So what's the algorithm going to look like? I'm listening. What's the algorithm going to look like? Qj depends on all the other QIs, which also need to be updated. So how do we work on this algorithm? We iterate this, right? And we iterate, and when do we stop? What's the buzzword that people in physics use, and you should be using here? It's not like you iterate until convergence. They don't use the word convergence. What do they use?
Self-consistency.
Thank you, self-consistency. All right, so I hope you're self-consistent as well. Okay? All right. So they iterate this until self-consistency. I am not going to discuss the implications of this in extremely significant applications like in distributions defined over graphs, right? But let me just say that this thing leads to extremely efficient algorithms for doing inference, okay? So this is not just a formula. So you can think actually, if this distribution, it comes out that is, from the exponential family like a Gaussian, maybe this expectation that you see on the right-hand side, it implies take all the other variables and substitute them, for example, with their mean values. Right? So you don't even have to keep track of the whole distribution. You can actually keep track of the moments in doing the updates of each of these factors. Okay. All right, so we need to do examples, otherwise you're not going to follow this whole idea. So let's do a simple example. We have a bivariate Gaussian, two variables here, z1 and z2. It's a Gaussian like that. And so I want to approximate a bivariate Gaussian with an approximation that looks like this. So here there are no latent variables, but the idea obviously is the same. So I'm going to have an approximation of this distribution with a q of z that factorizes with each of these factors. Okay, q1 of z1 only and q2 of z2 only. Okay, so now I am not telling you that this factor is a Gaussian, this factor is a Gaussian. We don't know what they are. Okay, so we're going to try to apply the general methodology, the derivation of the optimal formula from this mean field approximation to see exactly what how each of these factors looks like. So these calculations, by the way, they may look very tedious, not for this example, for other examples. If you don't do every single calculation that's on the slides, you're not going to be able to actually apply this method to your own problem for your research. So if you hesitate to do algebra by hand, waiting to read it somewhere on the web, you are not going to go anywhere, not to mention the chances that somebody has put the wrong signs or the wrong subscripts is very high, like in my slides. And as a result, you will be complaining that something doesn't work when actually the mistake is rather trivial. Okay, so remember our optimality formula, right? The log of the optimal solution, and I put a star there, but since we will do it self-consistently, we don't have to worry about this. So the log of Q1 is the log of the joint distribution of Z, which is Z1 and Z2, averaged, where we average all the other variables. What's all the other variables here? If this is Z1, what's the other variables? Is Z2. Okay? That's our general formula. You remember? Yes, no? All right, so I don't need to go back. Okay, so this is the joint log distribution, right? And we average with respect to all the other variables. Because this is a bivariate Gaussian, I can take the exponent, every term that has the z's on it, and you get these two terms, plus constants, we don't care, okay? And we need to average this with respect to Z2, okay? So if you look everywhere there is Z2, there is no Z2 here, all right? Z1, we need to keep it because we need to compute this as a distribution in Z1. So Z1, we keep it. The constant terms don't really matter. And here there is a Z2, so instead of Z2, we're going to have to put the expectation of Z2. Okay? Now, if you look carefully, what you have here is a Z1 squared term, and then you have a Z1 term, right? Plus constant. So obviously, this is what type of distribution? So immediately, you can see that Q1 is what? Gaussian, thank you. And it comes out that the Gaussian has this, for Q1 has this mean, all right? And the variance here, or the precision, is lambda 1, 1, okay? In terms of the precision, so lambda 1, 1 comes from the partition of this lambda, and then the distribution for C2 comes to be having this mean, all right? And precision lambda 2, 2, okay? So effectively, somebody will say, you know, I can do iterations here, right? So if you try to approximate this, what you need to do is you need to know M2. So you know, obviously, when you approximate Q2, this will give you M2. So if you have an estimate of this, you can plug it in. You update Q1, so you update M1, and you see there is an M1 here. Is there anything you have to worry about this trivial problem? In other words, if somebody tells you, I don't believe there is self-consistent solution here. In other ways, if I start iterating M1 and M2, I doubt it there is a fixed point calculation there. And so what would you say to verify if there is for this simple problem or not? You notice, right, that this thing here requires M2, and I have a formula for M2. So what can you do? Put the two equations together, all right? And you can show that the solution, that the only solution you can obtain when this thing reaches self-consistency, okay? So there is a self-consistency solution is if the mean for the distribution Q1 is mu1, all right? And the mean for the distribution Q2 is mu2. You can verify this. Okay? So effectively, basically, the solutions you will get, it will look like this and will look like that, which is actually sort of the obvious approximations using the partition of the mean and the partition of the precision. In general, we're going to have to solve these equations iteratively. Okay? So I am not quite sure if actually the links work, so I'm going to have to check later today or tomorrow, so I will update them. We are trying to approximate this distribution P of Z with a factorization that we just discussed, all right? So I think, I'm guessing, this is what the solution that you get, okay? So you can see when you minimize basically the KL distance from Q to P, okay, the forward KL distance, basically the support of the distribution Q is defined by the direction of the smallest variance of P of Z, and you can see the variance is underestimated in this direction, okay, is underestimated. So actually, in some sense, in these regions where P of Z is small, all right, Q of Z is equal to 0. Can you actually think of the formula why maybe that happens? So in the regions where P is 0, Q, in the regions where P is very small, Q is 0. Remember, we have to minimize what's the KL distance, right? Involves Q log of P over Q. So if P is small, all right, to minimize what has to happen to the ratio P over Q. If you have something small divided, you know, by Q that is 0, what do you get? If you have P over Q, right, and Q is not 0, what do you get? Have log of P, a small number, divided by Q that is non-zero. What does that give you? What's the log of 0? Huh? Big number. all right? You cannot minimize that, that's not good. You cannot be an optimal solution. So to do this minimization of the forward distance of KL distance from Q to P, in regions where P is small, the distribution Q has to be equal to 0. So remember this picture, because I'm going shortly to reverse the minimization problem to do further things with variational methods where we may get something, something different, okay? All right, and here actually is the something different, okay? And we don't have time to do all the mathematics here, right? But what I'm gonna try to do is, since we pose the problem with this lower bound and then it was equivalent to minimizing the distance of Q from P, someone will say, let's forget the lower bound. How about if I minimize the distance of P from Q? Right, and this is not a symmetric distance, so it will give us something different here. So if you minimize the distance of P from Q, this is how the KL distance looks like, or it looks like that, okay? How about, okay, if I tell you that following the algebra simply, all right, and isolating one factor at a time, and the only trick you have to do when you optimize with respect to Qj is you need to enforce a normalization condition. You get the following result that you see on the bottom, that it says the optimal Qj is equal to P of Zj. And P of Zj, it's the marginal of the distribution P. So the optimal solution here is the marginal, which means no iterations are needed, no need for self-consistency or anything like that. So the optimal Qj is the marginal of Zj, okay? Just by reversing the distance somehow, things were turned upside down. And here is what we do. So this is the same problem. This is what we did before. We minimized the distance of KL of Q from P, and we got like this, and we discussed why here we underestimate the variance, Q is 0. And now, if we minimize the distance of KL from P to Q, in this particular case, we get something like that. So even in regions where P is small, Q comes not to be 0. And also notice, so this contours here, if you can see the colors, right? That's P of Z. In regions where P is 0, Q is not 0. Again, can you see why? In regions where P is 0, Q is not 0. Okay? You can see this. And it's basically the reverse argument of what we discussed before. Now, if you try to use this reverse KL distance for a distribution that has two modes, like a Gaussian with two modes, then something interesting happens when you minimize this KL distance. And so you see, you get a broad distribution, all right, that is trying sort of to mimic the whole Gaussian, all right? What do you think you will get when you do the maximization of the lower bound in this problem? So when you do the reverse KL distance, you get something like this. What will you get for this problem when you use the minimization of KL from Q to P? This is what you get, okay? So basically, the solutions you will get, it will either collapse on this mode or it will collapse on that mode. All right? It's maybe, you can put it in some similarity using the Laplace approximation to a distribution that has two modes. Obviously, you're going to capture one of the modes correctly. You're not going to capture the other mode at all. And this is what's happening here. You capture with the mean field approximation one of the modes correctly. And which one you capture depends, obviously, because you run this in a self-consistent manner, how the iteration proceeds, and it will give you this solution or it will give you that solution. The reverse distance basically gives you a much broader distribution that is trying to capture the mass of the distribution P of x. It has way broader support than the distributions we get in this case. And here I'm repeating the same example, basically showing to you the KL minimization problem where we minimize KL Q from P and also, I suppose, P from Q. Do you see anything like that? Does it say that? So this is the true distribution, this is the Laplace. I'm assuming this is the KL Q to P, and the blue is actually the KL P to Q. Does that make sense? And you can see that actually the blue distribution has a much broader, support than the red distribution, the way we described on the earlier slides. Okay. This problem I did with a Gaussian, actually. You can generalize it, and you can do this for the multivariate Gaussian as well, and so you can see those discussions in the slides. You may, so before I give you real examples of more complicated problems with these variational methods, you may ask, is the KL distance basically the ideal distance? It's like every time I give a presentation, somebody who doesn't know where the KL distance is, but he heard of all the distance, says to me, why you haven't used that distance? It's like they know how to do it, and so basically I always have to find a reason to respond and say why this and that, when the answer is because, well, things look simpler. Okay? So the other distances that generalize the KL distances are what's called this alpha divergence, that is defined with this coefficient alpha here, that goes from -infinity to infinity. And I am not going to go through the discussion. Actually, the calculation, it's very simple. It uses some asymptotic Taylor series sort of approximations. But this alpha divergences, when alpha goes to 1, you get the backward KL distance. When alpha goes to -1, you get the, there's a mistake here, right? When alpha goes to 1, you get the forward distance, so this has to be the distance of Q from P, okay? No, actually I'm wrong, I'm right. I mean, this is correct, right? What am I talking? This is the alpha divergence. So the alpha divergence, when alpha goes to 1, it gives you the backward distance. And when alpha goes to -1, it gives you the forward distance between Q and P, okay? You can actually, if you take this coefficient alpha to be equal to 0, you get what is called a Hettinger distance that you may have seen in different contexts, you know, and lots of these things are used also in network theory. So these are all the measures of distance between distributions. Now, the variational methods we discussed today, you can address them in the context of these distances, but don't expect to get any solution that basically looks, that has some intuition behind it, the way the main field theory has, or that the calculations are going to be simpler. So lots of these calculations will be way more involved. Okay. So let me not do this, the whole thing, but maybe you can help me to extrapolate on exactly what the variational method is going to give us for the following problem. You remember when we discussed about the expectation maximization algorithm, right? We had some latent variable z, and we had some parameters. So on the E step, what did we do? We computed the posterior of the latent variables, z, given the parameters, and then with the posterior of the M step, we computed the sufficient statistics, and then we maximized with respect to what? The parameters. So I want you to look now on a factorization of this problem that involves both the latent variables and the parameters. So basically the KL distance, the forward distance, will look like this, where I factorize with respect to the parameters, I factorize with respect to z, okay? And I am going to actually take the distribution Q of theta to be a delta function. I want you to tell me if I plug in all of this and I repeat the lower bound or the KL distance minimization, what do you think the answers are going to be for this problem? So if we plug in, we try to find, right, an approximation, actually I should put a theta there, an approximation of the joint posterior of the latent variable z and the parameters theta, okay? And I'm going to factorize this following the mean field approximation as some distribution of z times some distribution of theta. And for practical purposes, for making a point, I can use anything I want for the distribution of theta, right? I can put in an arbitrary distribution and optimize, but I'm going to take the distribution of theta to be a delta function. So can you envision on what, when I plug in all of this and I minimize this, what do you think is going to come out at the end of the day? What will be the final, how will the mean field approximation look like? What type of results is going to give me? I just told you what they are.
Mean field over the latent variables.
Say it again?
Mean field over the latent variables.
Yeah, I know, mean field over the latent variables, but will it give us something? We already have discussed it and you have worked on it in your homework. Will give the same results as what algorithm? Which one? The EM. All right, so this will be basically, we will get the same identical results as the expectation maximization algorithm, which means that obviously these sort of approximations are way more powerful, way more general, right? Because here we are looking for Q of theta that is a delta function, okay? All right. So you can generalize this basically, but what you get out, you get results that look the same, basically are the same as the expectation maximization algorithm. Okay, so I'm not going to discuss this, so you can guys read this more. Okay, so let me do one practical example. There are hundreds of examples in the notes, and some of them are very fundamental, basically, because the algebra appears in multiple fronts in machine learning. So, but let's do some trivial example of using, since we talk about the mean field approximation, this is the example you will see in statistical mechanics books, okay? So imagine that you have these nodes here, and each node represents a spin variable. You can think of a magnetism model where each variable is spin up or spin down, plus minus 1. All right, they're binary variables. And these y's are observations of these binary variables that they're noisy. Right, so it's obviously a trivial model, but somehow the fact that I have connected all these variables like that means they are correlated. Okay, so the joint model of x and y looks like that. Okay, and so the distribution p of x, okay, I am going to write it as a Boltzmann-Gibbs distribution, right? We already have used this many times, using an energy functional, all right? So p of x is going to be written as e to the minus this energy, okay? And hopefully I have not done a mistake here on the signs, double dipping in the signs. Okay, we will see this shortly. Where when you see an energy functional like that, right, it tells you that the nodes I and j are correlated with some way w and I and j, but only neighboring nodes are correlated. All right, so what j is a neighbor of I, okay? Makes sense, right? I mean, you have, if one node has a spin up, there is a higher chance the next node we have spin up, and this type of interaction captures that, okay? So the distribution p of x is given e to the minus e0, okay? And this is sort of a normalization factor. Okay, and we have a likelihood model because we have these observations y, and these observations are IID, so given an x, the likelihood for y given x is written with, each of these terms will be an exponential, and a product of this will give me a summation inside the exponential, and I define another likelihood energy function that I call it Li. Okay? They are parts of the model. So this is a likelihood model, all right? What's the probability of y given x? I define it with this energy functional, all right? And I put it in this exponential form, and you will see shortly why. And then the distribution of x, which is my original variables, I write it using this energy functional that you see there. So if I put all of them together, you can see basically that the joint distribution of x and y, if I don't pay attention to the normalization factor, is e to the minus e, all right, where e is E0 minus the summation of these local likelihood functions. So basically you get an energy potential that drives the joint model of x and y. All right. So what is the objective? What is the problem we want to postulate? So this is the original model, right? This is the joint distribution, so the anomalized joint distribution of x and y. So what do we want to compute? We want, given the y's, that they're noisy data, noisy observations of the x's, we want to calculate the distribution, the posterior distribution of x. So what we're going to do is, we're going to do a mean field approximation. We're going to write q of x as with a factorization where we get one contribution I for each node xi. So we're going to approximate the posterior distribution of all of the x's given the y's, factorized as such. Okay? I am, let me see how much algebra we can do. Okay? So will you agree with me? Look at this formula and tell me from where this formula is coming. With all the notations we have used up to now. You remember we had defined when we did this mean field approximation, this peak early, and log of peak early was what? In this particular case, it was minus the energy functional. So it was actually minus the log of the joint distribution of x and y. And if you see here, it is given as xi times wij xj for all the neighbors j of I, plus this functional li. If you want to study the slide, right, and see the exact calculation, I'm going to give you the formula so we can see if the formula makes sense. So it comes out that the exact distribution, or the posterior distribution for each node xi, is the exponential of xi times the summation of wij times the means of xj, where xj's are the neighbors of I, plus li, which is a function of xi. So can you tell me where the mean field approximation appears in that formula? I mean, what is it in that formula that somehow reminds you that this is a result of a mean field approximation? You remember q of xi is the average of the joint distribution of all the other variables, right? Average with respect to what all the other variables are doing. So what I have done here is, what have I done to all the other variables? You substituted them with the average, because they're binary variables, so when you take expectations, you get the average. Okay? Q of xi looks like this, and you can actually put these things in a very nice form. I strongly advise you to look at this example, and at the end of the day, it comes out, all right, that you don't really need to keep track of all of these distributions exactly. The only thing you need to keep track is the means of these distributions, because the variables are binary here, so you need to keep track of the means. And the update formula for the means, that you have to do it in self-consistency, is given by this nice formula, okay, where Li plus and Li minus are basically these likelihood models when xi is equal to +1 or -1. So you basically have a nice update formula to update the means. So where can I use all of these things? You know what? You can do actually simple things if you want to do a denoising of an image. So if I give you that this is the y of the image, right? And the image is black or white, so it's a binary. So what you need to do is you need to actually find me the posterior of the x variables given these noisy observations y. So if you take, literally, come on, if you take this algorithm here, one line, and you start iterating on the mu's, okay? So in the image that I showed you, every pixel is one eye, right? It's one node. So if you start iterating, after 3 iterations you will get that, and after 15 actually sweeps through the image, you actually get the original image A. Okay? So effectively, you can see the mean field approximation in action in doing denoising or deep learning of images, and you can think of many, many other applications where this thing can be extremely handy. Okay? All right, I know I need to stop at some point. Okay, so this is a wonderful example, but it's beyond, it's far and beyond of what we can do here. Okay, all right, even though I took it up today. Okay, so let's, let me just finish with another trivial example. Actually, I'm going to bypass even this example. Come on. I wanted to revisit some of the examples we have seen. Okay. Okay, this is exactly what I wanted to do. Okay, so let's very fast, right? Go and revisit something that is trivial and we have seen it 1,000 times, right? So this is our typical regression problem with some regression coefficients W, basis functions phi, some noise variable beta. We put a Gaussian prior on W, and I put a prior actually on the hyperparameter that's a gamma prior. Okay, so the question is, how is it possible that maybe this mean field approximation, this variational Bayes, can actually be used in revisiting everything we have done in this course? And the answer is simple. You say, look, in this problem, what I have is I have the observable variables, and then I have a lot of unknown parameters, the coefficients W and the coefficients alpha. Okay? So this is basically my joint likelihood. Okay? And you can factorize it as the likelihood model if you knew W what T would be, and then the prior of W given alpha, and then a prior on the hyperparameters alpha. All right. What are the unknowns that we worked on this when we played with regression problems? The unknowns were W, and the unknowns were alpha. And I'm not even sure actually if in the first model we did, if we took alpha as constant or we computed alpha. But here we take both W and alpha to be unknowns. All right, so we need to compute, given the observations T, we need to compute the posterior of W and the posterior of alpha. All right, we have seen these results. So what we are going to do is with the mean field approximation, we're going to take the joint variational approximation of W and alpha, and we're going to factorize it as Q of W times Q of alpha. And we're going to ask, give us what are the self-consistent, the iterative scheme coming from mean field approximation that will allow me to update Q of W and Q of alpha. Okay? The algebra is extremely simple, right? What do you need to do? Can you remind me what is the, so this is the joint this is the joint likelihood. So what is the algorithm that will allow me to get Q of W? What do I have to write down basically that will give me a formula for Q of W? Remember, we have to maximize the lower bound, right? And the lower bound, actually I don't have to maximize anything. We already know the answer. What is the answer for calculating Q of W? From mean field approximation. What do you need to evaluate first to compute what Q of W is going to be? So log of Q of W would be what? You remember the formula I had for mean field approximation? What was it? We have to find the joint log likelihood, which is here, all right? And then take the expectation of that with respect to what variables? To calculate Q of W. All of the other variables. And what are all the other variables in this problem? Alpha. Okay? And here's what I do. Okay? For example, actually, I'm going to do this in first for alpha. Okay? So to calculate the optimal Q of alpha, what I have here is log of P of alpha plus the expectation with respect to W of this term plus constants. Can you tell me where this term came and where that term came? Where did this term came and where this term came, right? That's the alpha dependence. All right, you notice? So I have to take the log of this and the log of that, and this term that involves the log of this Gaussian is a function of W. So everywhere we see W, we need to do what to the W? You remember expectation with respect to, if I'm going to calculate the optimal of Q of alpha, I'm going to have to take the average with respect to all of the other variables. So where I see W, I have to take expectations with respect to W. So if you write this formula from mean field approximation, immediately you can see this gamma distribution. If you actually do the same thing with Q of W, take the joint distribution, every term that has W in it, and everywhere you see alpha, you have to take expectations with respect to alpha, and when you complete the square, there is the variation approximation for the posterior of W. Interestingly, the results are identical with what we have seen before in using Bayes rule and all the standard things. The only difference you can see here is where we have alpha, there's no alpha anymore. It's the expectation of alpha. And where there was W, it's not W anymore, it's the expectation of W. Okay? So this type of approximation actually is way more powerful than the type of things we have seen before. And of course, this generalizes things we have seen earlier. And something that you need to do in all of these problems, you need to verify to yourselves that whatever approximations you start doing, and you start iterating self-consistently in finding these Q factors, at all times, you need to plot the lower bound. And if the lower bound doesn't increase monotonically, there is a mistake. I mean, you can read it even explicitly in a 20-year-old book in Bishop. It says, plot it. If it goes down, you have a problem. Okay? So in this case, you can actually compute the lower bound analytically, and it comes out. You can get a closed, basically form solution for all the terms, and you can plot it. And if you plot it, you can actually problems we discussed in earlier lectures about model selection, what's the order of polynomial and things like that, you can address them with variational methods. All right, is 128, so what I'm going to do is I'm going to stop here. You read the rest of the slides.